So normal distribution is defined by its mean and standard deviation. So when we talk about something having a normal distribution, we usually state two things. We state, hey, here's its mean and here's its standard deviation. Remember when we talk about standard deviation of a sampling distribution, it's called the standard error. So standard error, error is the standard deviation of a sampling distribution. So if I take my mixed nuts, for example, sampling distribution, and that sampling distribution was for the proportion of peanuts. And again, what does that mean there? So whether something is a peanut or not, that's a qualitative variable, a categorical variable, and we can't do a mean on a categorical variable because you can't just add up the word peanut, 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 peanut. Doesn't make any sense. But you can say, hey, there were 240 peanuts and there were 357 nuts. So a proportion is kind of like a mean, but for a categorical variable. And in that distribution, I had a mean of p hat of about, was it 67%? Double check that. This is the one. Yeah, 240 out of 357 is about 67%. And according to StatKey, the standard deviation for the sampling distribution is about 0.025. And so that would be the measure of its spread. So to define this particular normal distribution, I just need to know its center and its spread. In this case, its spread would be this standard error, which is 0.025. And abbreviating that, we'll often write something like n for normal, parentheses, and then we'll state whatever the parameter is, the mean or the proportion. And then we'll state whatever the standard error is. So in this case, for the mixed nuts, I would write n 0.67, comma 0.025. And then to do something with that, I need a normal distribution calculator. And StatKey can do that, a spreadsheet can do that. So those are the main two things that we're going to look at. So over here, I can kind of use StatKey's ability to do right tails and left tails. So if I put, say, 5% in the upper tail, oops, not 50%, 5%, please. Find the right spot here. Yeah. 0.5, there we go. That's better. So if I put 5% in the upper tail, StatKey tells me that the value that goes with that is 71.4% mixed nuts. I could put 5% in the lower tail. StatKey says that would be having 63% peanuts or less. And so here what I'm creating is a confidence interval. 5% in the left and 5% in the right puts 90% in the middle. And so that means I expect, based on this sample, that this company has somewhere between 63 and 71% peanuts based on the way I counted the peanuts. Now, then we would have to say, well, how do they count the peanuts? That's a whole other thing. Maybe they counted them by weight. And I have to wonder, is the density of a peanut different than in, what else did they have in there? They had almonds, they had Brazil nuts. Somebody stole my sample and ate some, so now I can't weigh them, darn it.
I ate all the cashews.
There's cashews in there.
I ate all of the cashews.
You ate all the cashews, damn you. Sorry, one of my colleagues just borrowed my mixed nuts. Now I lost track of what I was saying here. Oh yeah, so how did they count the mixed nuts? I thought my effort was reasonable to count all of the nuts and then estimate how many of them were whole nuts. Anyway, so I think there's somewhere between 63% and 71% of mixed nuts here. And these numbers here are a certain percent away from, or certain distance away from the mean. Standard would be to do a two-tail, right, when we do a confidence interval, put 95% in the middle. So we would expect this 6.25, 62.5% to be about 2 standard deviations below the mean. So I just want to review that idea. So this is a 95% confidence interval. And based on that 95% rule, this number here should be about 2 standard deviations below the mean. And this one right here should be about 2 standard deviations above the mean. This idea of counting standard deviations is called a z-score. We talked about that way back. So counting standard deviations. Is a z-score. And the technical way to do it is to take whatever measurement you have. So in this case, I have my, my value for P here, and then I have my mean over here. So usually we write something like the X value minus the average X value, right, the number in the middle, divided by the standard deviation, which is often called S. Now, my numbers are a little bit different. I'm talking about means in this case. So the z-score in this case, so I'm going to say X equals 0.72, and that extra 0 is not relevant. My mean here, that's the middle, 0.673, so that's my X bar. And my standard deviation, that's the standard error, so that's my S right there, 0.025. So let's double check the z-score of this value. The 95% rule says it should be about 2. So to calculate the z-score, I take my X, 0.72. I subtract my mean, my middle, 0.673, and then I divide by the standard deviation, which in this case is the standard error. All right, so with that on a calculator, see if it is close. Calculator off to the side here. All right, so here's my calculator version of that. For this particular randomization, I get 1.88, which is close to 2. I could round that up to 2. So it's about 2. Is it going to be exactly 2 standard deviations? The answer is no, because of the randomness going on here, but it should be close. So I got 1.88, which to the nearest whole standard deviation is a 2. So z-scores are what we're looking at here. So z-scores for a proportion are going to look something like, usually it's going to be p hat minus p over whatever the standard error is. So that's the calculation I just made. But we could have a z-score for a mean, which is pretty similar, same idea. It's whatever number I'm interested in minus the center divided by the measure of the spread. So it would be something like an x bar minus a mu divided by that standard error. And in general, for a z-score, so that's a mean, we got some value of interest minus whatever the center is of our distribution divided by our measure of spread, which is always some kind of standard deviation. We just got to put the right one down there. For most of the work we do, our standard deviation is going to be that standard error. 99% of the time. So what I want to do is I want to check on a normal calculator to see if I get similar numbers to when we run a stack key simulation. So we're just going to go back and look at a different example. Actually, we can do this one right here. So we can take these numbers right here and I'm going to sketch it out. So this is the idea of a theoretical normal. Theoretical normal distribution. And so that's anytime I draw out this smooth curve right there. So for the one I'm looking at, I have 0.673 there. Out here, I had 0.72. Check. Yep. And my standard error I also need to know for this. Standard error 0.025. So for most normal distribution calculators, and we could use a spreadsheet or stat key is easier, but it only gives us limited options for the decimal values. So back to the stat key homepage. Let's see, we want theoretical normal. I'll put this in the chat so you can give it a try. Sorry to hear you're allergic. Oh no. Do you ever see cashews grow? They're so weird. All right, so this is the theoretical normal. To use the theoretical normal in stat key, you have to enter the right mean and standard deviation and then choose the right tail, left, right, or two tails. Now, whenever you have a 0 and a 1, that's the idea of what we call a standard normal. It just counts z-scores. I'll go over that in just a moment. And I'm going to enter my parameters here. So mine would be the mean of 0.673 was the one on my sampling distribution. And the standard error is the standard deviation there, 0.025. So I'm just going with that same example. And then I'm wondering about 0.72. Where does that live over here? How far over is it really? So it's to the right of the mean. So I choose right tail. And then I just go down here and type in my number, 0.72. And stat key says it leads to a probability of about 3% in the right tail. So if we expected the mean to be 0.673 and we think the spread is 0.025, then we expect that about 3% of the time we'll end up with a proportion of 0.72 or higher. Right? So that's that idea of a p-value that I'm talking about here. Now notice that's a little bit different than over here. Here stat key matched 0.025 with 7.2. So that's not quite 3%, that's 2.5%. Chances are if I resample it again, reset, Still have my mixed nut data there. So with something like a proportion, we don't need all the original data. We just need to know what's the counterfavorable, what's the sample size. And then if I go over here, just looking at the right tail again, this time 0.72 still came out to 0.25. So there's always going to be a little bit of difference between the simulated versions of these values and the theoretical versions of these values. It's like, again, if you flip a coin 100 times, do you expect to get exactly 50 heads and 50 tails? The answer is no, but they should be kind of in the ballpark. 3%, I think, is in the ballpark of 2.5% for 72. If we went for 3% here, it still says 72 down here. It didn't have enough significance in the 4th decimal to change this number down there. So they're pretty similar.